Okay, so let's remind ourselves. So last time we're solving the Schrodinger equation in spherical coordinates, which is complicated, r, theta, phi. And we found, if you remember, that the phi equation, let me write it all down, that we had broken up the spatial wave function into r of r, theta, capital theta of theta, capital phi of phi. And we found phi, we stuck the label m on it, and it was just this. E to the integer times phi, the angle, with m taking those values. We also found theta that depended on a number that we called L. Remember, there was a constant C, and then we said C was equal to minus L times L plus 1 for reasons that were maybe a little bit mysterious, but the point was that L was an integer and C was that number, L times L plus 1 with a negative sign. And I also argued that L was typically the highest power in sines and cosines raised to a power. And I know that I just told you that, but again, you would find that by painstaking work of exploring solutions of various arbitrary power of cosines and sines, plugging into that messy equation for theta, and just finding relationships that make the solutions work. And those are called Legendre polynomials. And so that's where we took it. And I wrote down a couple of these thetas. And it was also true that in order for theta to work, we then got a rule on the n sub L. This one up to ... up to plus or minus L. Before we didn't have that. If we just considered this alone as a solution, it was any integer. And this had to be an integer just simply so that if you went around in a circle, the wave function had the same value when you ran around once. But when you consider this thing, then m sub L had a rule. A thing that I might give you on an exam is give you some version of one of the Legendre polynomials, one of these solutions, and say, show that it works out. Okay? You saw the algebra I had to do. That's the sort of thing that I think is fair, because the point of this class is not to go through and prove that the actual mathematical forms, and they're listed in the book, are the solutions, but I certainly want you to understand where they come from. It's not beyond you at all to prove it. It's just more work and more time than we can afford to spend given what we're trying to do in this class. Okay? So I have to, you'll just have to accept a little bit that that's the way the algebra works out. Now, okay, so that's fine, and this is where we are, and it's these are a bit mathematical. Can we get any sort of physical sense of what's going on here? First off, let me make an argument about this bit. One thing I said already, and let me just repeat, is that phi star phi equals 1. Okay, so if I ask, clearly, right? And so if I ask about the probability of the particle having some value of phi, the answer is it's uniform. In fact, if you graph the solutions we had, they are either like spheres, where this is the z-axis, that's y and that's x, like two spheres like that, or there are lots of solutions. By solution, I mean I'm plotting the product. I'm plotting this times this squared. but that's just 1. So I'm really just plotting this, the Legendre polynomial. There's ones that are donuts. Not sure I can draw a donut very well. Donuts, right? And you may have seen these in your chemistry class. These are the famous orbitals in an atom. They're all symmetric around Z. But, you know, it does feel like it's rotating. Again, this thing is not a real physical rotation, but it kind of seems like it's rotating. So let me make a hand-wavy argument as to what that phi represents, and then I'll make a hardcore technical argument. Okay? The hand-wavy argument is, if I'm sitting here in the plane with a radius r, if I go around once, the circumference is equal to 2 pi r, obviously. And the way that e to the I have e to the I m sub l phi, if m sub l is 1, that means the phase changed by 1. I went through 1 cycle of a sinusoid as I went around. If ml was 2, I went around 2 cycles of a sinusoid. So let me say in some sort of vague way, that's saying that I stuck a wavelength into this thing as it went around. All right? And if that's true, there's a momentum, which is h over L, h over lambda. Let's see, 1 over lambda is ml over this stuff, h ml over 2 pi r. Okay? And then if that's the case, well, that's just h bar, and let me multiply by r on both sides. Rp equals h bar m sub l. And what's r times p? Well, if I had r here in the plane, that's just the angular momentum around the z-axis. If something is kind of zooming around, I would identify that with the angular momentum on the z-axis. Now that's a hand-wavy argument. I'm about to make it much more concrete. But it turns out that is the right answer. So this phi wave function, which disappears when I really take a probability, somehow represents the fact that the particle has angular momentum about the z-axis. Okay? Let me make it much more serious argument. Let me start with a guess, and then I'll show you that the guess was right. Let me guess that, in fact, I should have a quantum mechanical angular momentum operator for the z-axis, which by analogy with normal momentum, which was h bar over I d by dx, let me just guess that this is h bar over I d by d phi. All right? If that's the case, just think about applying Lz times phi sub m. Let me just take the derivative of that, and clearly I just get, and that's h bar. It is h bar, that is m sub l, h bar phi sub m, right? You can see that. Straightforward. This would be to say this is an eigenstate of that function. Okay? Now let me prove that this is the case. How will I do that? I have d by d phi, and I want to deal with that. And I'm in these kind of nasty spherical coordinates. Let's remind ourselves what we're doing with that. We have x, we have y, we have z. We have a vector r that comes down from z at the theta, and then has phi like that. So x equals r cos theta, r sine theta, the projection into this plane, times cos phi, because phi is that angle. Y is r sine theta. There's certain things you end up committing to memory that you don't think originally you're going to. If you guys stick in physics, you're going to have this in your head. Y equals r sine theta sine phi. Z is r cos theta. Okay? So let me express d phi in terms of x and y. How do I do that? If I have a function of theta, or actually of z, of say x of theta, if I do df d theta, that's df dx dx d theta, right? So I can think of d by d theta as being dx d theta d by dx. This is just sort of chain rule of calculus, but you may not have thought of it exactly this way. And so even though, with apologies, some of you may not already know this, I just wanted to repeat that. So that's how I'm going to switch from one coordinate system to the other. D by d theta, I do dx d theta, d by dx. So d by d phi is dx d phi d by dx plus dy d phi d by dy plus dz d phi d by dz. I have to do all of this because if I'm going to look at the derivative of the wave function with respect to phi, and I want to relate that to angular momentum in z, I want to talk about x, y, z. The wave function can depend on x and y and z, and so this is how I would work it out. All right? Now, over here, I can do these things. I want to do dx by d phi. So I just have to take this equation, and then dx d phi is to take the partial of this with respect to phi. So that's just r sine theta sine phi. Derivative of cosine is negative sine. And in fact, that is minus, that's just minus y, just because that is that. Similarly, dy d phi is the derivative of this respect to phi. I think you can see it's r sine theta cos phi, which is x. Finally, dz d phi is what? It's the derivative of z with respect to phi, and there is no phi, so it's just 0. So this is just simply dx d phi was minus y. dy d phi was x. Now that was just d by d phi. I really wanted to multiply by h bar over I. Okay. H bar over I d by dx is p sub x. This is minus y px plus x py. Right? Because px is just h bar over I d by dx. So like magic, so this is just rearranging the terms x py minus y px. You do remember this. Let's just do a refresher in case that was at all unclear. Remember what angular momentum is. Now, angular momentum, it's a measure of how fast you're rotating. And so there's two components to angular momentum. How fast am I rotating, but how far out am I, right? It's very different for me to take the chalk and rotate the chalk around right here than to put a chalk out at a distance and rotate it around. And of course you know the whole effect where if angular momentum is conserved and you, like you're a skater and you pull your arms in, it speeds you up and whatnot, okay? And so it's mathematically r cross p, which is I, j, k, x, y, z, px, py, pz, where I take the determinant. And so the x component is y No, the z component is xpy minus ypx. Boom. Oh, and these are operators. Okay? So it works out. It works out. And this is really, really nice because it's going to allow us, it's nice in the sense that it's just mathematically nice because instead of worrying about this d by d phi of the wave function, I just say, oh, that's just the L operator, and all the solutions to the Schrodinger equation are eigenstates, of L sub z, okay, and they have eigenvalue m sub L, as I said, and this is to say that when you're in an atom, the angular momentum along the z-axis is determined, okay, and you may have well learned this from your chemistry class. All right. Okay, fair enough. So that's what's going on with z. What about x and y? I cheated here with z. I cheated here and I guessed what the form of the z operator should be, and then I worked out d phi in terms of x's and y's. You don't have a good guess as to where to proceed with the x and y. We really can't do it this way. If I wanted to do this game, well, if I really want to work this out, it's quite a bit of algebra. And in fact, it's so much algebra, it is in your book. It's in Appendix G. And yeah, just take a look, okay? I want to give you a taste. I don't expect you to read Appendix G, although I would recommend it. If you're having trouble sleeping. No, I mean, I love this stuff, but I would recommend you at least look at it. But okay, let's just take a look at how it will work out. So let's look at what the Lx operator ought to be. Let's start with Cartesian and go to spherical rather than starting with spherical and going to Cartesian. That's algebraically a little more cumbersome. I ought to be able to go either direction. Okay, so I know that it's ypz minus zpy. It's ypz minus zpy, which is h bar over I y d by dz plus z minus z d by dy. All right? And now I want to translate that over to r theta phi notion. So let me see, like for instance, if I take the term y, I can nicely just write down y in terms of r theta phi like that. But I've got the d by dz. Using the same notion of chain rule in calculus, d by dz is going to be dr by dz, d by dr. So the z derivative will be the r derivative with this coefficient out front, plus a theta derivative with that coefficient, plus a phi derivative with that coefficient. Okay, I got to find dr by dz. Let me do a couple of these as an example, and then I'm going to stop and punt and write down the final answer. But I don't want it to seem like magic. I want to show you where these come from. So I want dr dz. I could try something. Here's an equation with r and z. That looks good. R equals, z. Well, rearranging it, z, r equals z over cos theta. Okay? So I can try, let's take the derivative, the partial with respect to z. Let me put a question mark there. Is that right? Just partial with respect to z. On this side, there is a dr to z. On that side, I see z, and take the derivative of it, I get 1. That's not right. Do you know why it's not right?
You didn't derive with
Exactly. My three independent coordinates are either RZY, or x, y, z, or r theta phi. So theta dependent on z. So I can't do this. I need to end up with an expression that I have r expressed purely in terms of x, y, and z. Okay? And so that is simple. R equals the square root of x squared plus y squared plus z squared. Okay? So dr dz is 1/2 1 over the square root of x squared plus y squared plus z squared times the derivative of z squared, which is 2z. This is z over r. And now I want to write it in terms of r theta phi, and z is r cos theta. So it is just, in fact, cos theta. Okay? That's what I have to do. That's this guy. Now I've got to do that one, d theta dz. How will I do that? I can say, to get d theta dz, I can say cos theta equals z over r. Is z over x squared plus y squared plus z squared to the 1/2. And I take the derivative of this with respect to z and the derivative of that with respect to z, and I work it out. Okay? So on this side, I would get minus sine theta d theta dz. And on this side, I won't work it out, but I will, I can use the, I'll get this squared in the denominator, and then this times the derivative of that, which is 1, minus that times the derivative of this, which is going to be minus z over r again. Blah, 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 blah. Okay? And this is tabulated in the back of the book. This turns out to be that d theta dz. You do all that, and you end up with terms like r and z, and then you plug back in for their r theta phi equivalents. And d theta dz actually turns out to be simple in this case. It's minus sine theta over r. Okay? Also, d phi dz is easy because from these two expressions, you can see that tangent of phi, dividing this equation by that equation, r and sine theta cancel out. It's equal to y over x, right? It was just down in the plane that I had the phi defined. And so if I then take the derivative of this with respect to z, the derivative of that with respect to z is 0, so the d phi dz is 0. Finally, d by dz, just this term alone, is, just so you can see it, well, let me not just write that term. Y d by dz, okay, and h bar over I times it. So this first term, I'll leave off the h bar over I. So y d by dz, and y is r sine theta, sine phi, okay, is minus sine theta d by d theta minus cotangent theta was cosine of phi. All right. No. Sorry, that. What that is that's L sub x after I've done more algebra. So I'll just stop there. I plug these things into this. I plug these things into that. Each of this had 1, 2. Well, the third term was gone, thankfully. The same over here. I'm going to get 1, 2 terms. The third will disappear again. 4 terms. Collect terms. Okay, I get to there. And when I write it this way, I do have h bar over I in front. Oh, and this is d by d phi. I didn't finish writing. I don't want you necessarily, I mean, you certainly don't want to remember that, okay? But I want to make a point here. This is what L sub x is. It's a bloody mess, okay? And it's got a derivative with respect to theta times sine theta, apologies. A theta function, a phi function, then a derivative with respect to phi. Most emphatically, and this is the take-home message, or two take-home messages. This is the first take-home message, not a somewhat less important message, but still important. Lx times theta of L, m sub L. And in fact, I don't want to think about operating this thing only on the theta, because it has a phi derivative component. I want to operate it on theta and phi. Is not a constant times theta L ml phi m. It's just not. I mean, go back and look at one of the functions we did last week. I mean, the simplest one was, for instance, cos theta for this and nothing for that. And if I take this thing operating in a cos theta with no phi part, it was m sub L equals 0. That term is 0, but then I have d by d theta of cos theta is sine theta. The answer is that it's sine squared theta, which is not a constant times cos theta, right? So it just goes through and through. So Lx and Ly is similar. The formula for Ly is actually identical. The cosine theta part you might expect is the same, but right here I get a sine phi, which isn't surprising given the way I constructed x and y, and they only showed up in sine versus cosine of phi. But you can prove it to yourself. Both Lx and Ly are not eigenfunctions. For theta of L, m sub L, and phi sub m. Okay? So the mathematical statement is they're not eigenfunctions. The physical statement is that, and this is kind of weird, and I want you to really wrap your head around this. Let me erase this so I can draw a picture to talk about this. Before I draw the picture, I want to mention that, just repeat that LZ is an eigenfunction of, actually I only care about this bit, phi sub m, and the eigenvalue with value m sub L times h bar. Okay? So what is that to say? Angular momentum is a vector. Okay? Do you remember how that works? If I'm in a spin like this, I take my fingers and I curl them with the right-hand rule, the angular momentum vector points straight up. Okay? If I do some precarious weird thing and I spin like that, right, my angular momentum vector was doing that. All right? So here's my angular momentum vector, which means I'm effectively, you think I'm spinning around it. The point is that quantum mechanically, the amount in the z-axis of this thing has a value. It's an eigenstate, whereas x and y don't have a specific value. So that's to draw a picture where essentially I'm saying I have a vector. I don't really know where it is in x and y, but I do know where it is in z. And as you'll see, and I haven't shown it yet, we know how long it is. It is the length is an eigenstate, and I'll talk about that in a second. So I know the length of the vector, and I know its z component. And its z component takes on discrete quantum values, magnitude h bar, and just one. This is a number that's 0, 1, minus 1, etc. So that's just to say boom, 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 boom. spun around. Right? So it's to say that the angular momentum, if I think of it like that, its projection onto the z-axis has a certain value, but in x and y, it's anywhere on the circle. And there's just these discrete values it can take in z. It can be 0, so it's somewhere in the xy plane. It can be down there, so it's down below, etc. So this would be, for instance, I have 1, 2, 3, 4, 0, 1, 2, 3. This would be L equals 3. So m sub L is going from minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay? And these are the rules. Are these rules familiar with you from chemistry class, high school, right? This is where it comes from, though. We're working it out very rigorously, except I've skipped all the algebra and told you to look in Appendix G. Okay? And then there's this weird thing. And this is the fact that I don't know what x and y are while I know what z is. That's what? That's just an example of the uncertainty principle. That's all it is. So the angular momentum has uncertainty principle idea built into it. I can know what the z part of the angular momentum is, but I can't know what the x and y part is. Which is, let me see if I can do this physically. It's a little bit confusing. So it's to say if I'm spinning like this, it's just weird. I mean, it's to say, so suppose the thing is spinning, so that its angular momentum is doing that. It's to say that I did know that it was somewhere in the, spinning like somewhere like that, but I just didn't know this part. I only knew that it was up. Or if his head was down and spinning, I knew that, but I just didn't know an x and y. And so it's just this weird thing. There is absolutely no classical understanding of why you would know the z component of the angular momentum and not the x and y. A final comment is z. Who chose z, right? I mean, is it like in every classroom, all the electrons have a spin which is oriented along the up axis in the classroom and not along some other axis? Of course not, right? I just pick an axis, I label it z, and then I will know the angular momentum that way. Alternatively, I could, and I won't talk more about how I would do it, but I could just, what am I trying to say? I could just relabel the axes, or I could have solved everything where I just said z is over here physically, all right? But then I just simply wouldn't know, or I could redo my definitions here so that the angular momentum was known along x and not y and z, or along y but not x and z. Okay, I can do it, but I only get to pick one axis. It's arbitrary, and I pick it, and that's that. Okay? Now, I had found, and I erased it. I had found Lx is h bar over I, this horror, minus sine theta d by d theta. Actually, it's not that bad. Cotangent theta, cosine phi, d by d phi, that's an operator. Ly is the same operator in terms of theta. But I have a sine phi where before I had cosine phi. Good enough, fair enough. And I know what Lz is. I already wrote that one down. That's just h bar over I d by d theta, d by d phi, right? What about the magnitude of L sub z? Okay. Let me see, I certainly don't want to get involved in a square root. L squared is Lx, L is Lx squared plus Ly squared plus Lz squared to the 1/2. Okay, but I do not want to get involved with the square root. So instead, let's look at L squared just flat out like that, right? And the notion that these are vectors still carries. I simply need to square that. That one's easy. That's, that's minus h bar squared d by d phi squared, right? H bar squared, the I squares to give me the negative sign, just like I did with P earlier, right? Lx, oy vey. I mean, it's minus h bar squared I'll write it down once. Minus sine theta, d by d theta, plus cotangent theta, cosine phi, d by d phi, operating on the same thing. Minus sine theta, d by d theta, plus blah, blah, blah. I get tired, right? But that means I have to take this derivative and multiply it by this term and take the derivative of sine and then take this derivative and multiply it by the cotangent, blah, 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 blah. And so if I do Lx squared plus Ly squared plus Lz squared, I think this takes up about 2 solid pages of algebra in, and Appendix G. And he skips steps too. He says, oh, I quit writing. All right, so blah, 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 blah. A miracle occurs, okay? And L operator squared equals, watch this, minus h bar squared. Let me not write that quite yet. It'll be anticlimactic if I don't remind ourselves. Let's remind ourselves where we were with the Schrodinger equation. Then the miracle will seem more miraculous. Okay? So remember, what I had was minus h bar squared over 2m del squared psi equals e psi plus u psi equals e psi. I wrote what del squared was in r theta phi. I wrote phi psi equals r theta phi capital. And where did I end up? I ended up with minus h bar squared over 2m, 1 over r squared, d bar dr, r squared dr, then there's, if I do it this way, there's theta and then there's phi. Often I divide it out, but here I'm just going to leave them in. Minus h bar squared over 2m, 1 over, here I'm going to combine 2 terms, r squared sine squared theta, d by d theta, sine theta, d by d theta of theta, and phi goes along for the right, and so does r. Plus 1 over r squared sine squared theta, d squared phi, d phi squared, and then I have r theta phi. You know, let me do this a little different. Take out that minus h bar squared over 2m. It's just going to multiply all of that. Okay, plus u r theta phi equals e r theta phi. I think I got it all right. This is plus. So this was this awful radial derivative. This was the awful theta derivative. What does L squared equal? It is equal to, there's an h bar squared just from this basic part of the definition, and the minus sign from the I. But the sine and cosine and whatnot are this. After I simplify all the terms that are accumulating when I work all this out. The miracle is that this, apart from the 1 over r squared, is this. It's exactly the same. Okay? L squared operator just explicitly found by going through the drudgery of working out all the partial derivatives and switching from spherical to radial to cylinder to Cartesian coordinates, worked out is 1 over sine squared. Oh, I got a sine. That's 1 over sine theta. It's 1 over sine theta d by d theta of sine theta d by d phi. It's just the first term there in theta, and then this is the term in phi. And that's what it is. Okay? I solved for theta and phi to solve this equation. Okay? So, I don't have to do any more work. Remember, well, a couple of things. So first of all, if I put in my solutions I found with phi being phi sub m, that phi sub m, right? Again, I'm going to do something you guys can't do on your page. The second derivative here of this was what? It was just minus m sub L squared. Okay? And then if you remember, let me just isolate this little bit. I'm going to forget the r part. What I had was that when I solved, or when I just told you, when I quoted the solutions for the theta equation, what I said was that that is squared. This is what we said. I said that if I operate on theta with this junk, and that goes along, this m sub L squared came from the second derivative of the phi part, it was equal to a constant, and I said the constant I'm going to call minus L times L plus 1, and just that worked out. Again, this is this operator modulo an h bar squared. So in other words, I mean, just stare at this and stare at that. This is basically saying L hat squared on the combination of theta and phi. I need the phi also to be there because this is the derivative squared of phi, which is going to make the m sub L squared appear, is there's an h bar squared here, and there's a negative sign. The negative sign kills that. Okay? I hope you followed that. It's also written down in the book. If you didn't follow every step of algebra, I mean, I think it's clear though. I hope it's clear. Is it clear? Right, what's going on here? That the L squared operator is the theta and phi derivatives that appeared in the Schrodinger equation. And so if I just isolate that piece of the Schrodinger equation, this is the part I solved when I did separation of variables. Just go back in your notes and see what I did, or look in the book. They end up with exactly this equation. It's only just a piece of the Schrodinger equation that I said had to be constant. I called that the constant. And that implies then that the L squared operator acting on this has that. So this is the other thing you've learned, presumably in a quantum mechanics class. So if this is the value, if the operator L squared acting on this does that, if I ask for the expectation value, okay, then that's going to be, I'm going to sandwich the L squared. Okay, just to write it out fully, I have to write theta star, phi star. I'm going to drop the L and M sub L subscripts. They're implied. I don't want to write them down. Now, we're not going to talk about this in this class, but you've probably seen, or maybe not. I don't know if you've seen it in your in three-dimensional calculus class. I have to integrate over the volume. We don't go into that. There's a way you do that. The solid angle, etc. But the point is, L squared on this just gave me this constant. And then I have this double integral of psi squared, and phi star phi was 1. And if you, I didn't talk about it much, but the way that this was found, just like for the spatial wave function, this was normalized all to give 1. Okay? It's always what happens with an eigenfunction. I'm just showing you what happens with an eigenfunction all over again. The expectation value is just the eigenvalue, right? And the other stuff goes along for the ride, and when you take the expectation value formally, the integral just integrates to 1 because that's how I normalize the wave function. So this we say, well, L is the square root. I mean, what it really is, quantum mechanically, I take the angular momentum operator, I square it, I take the expectation value, I take the square root of that, and we write that as capital L. That's the length of the angular momentum vector. Let me not write it there. Sorry, that was a poor move. Let me do it over here. So L equals the square root of L operator squared average. Average meaning taking the expectation value. That is just h bar times the square root of L times L plus 1. Okay? So now I've done it. I've thoroughly explored the theta and phi components. I haven't looked at the radial part. We'll do that next time. But let me just summarize. The solutions to the Schrodinger equation are theta sub theta, this theta piece, which depends on the angle from the z-axis. And it has two numbers associated with it. And then there's a phi piece, which has the number m associated with it. There are rules for m. And that's that it goes 0, plus and minus 1, plus and minus 2, dot, 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 up to plus and minus L. There's going to be a rule for L which relates it to the R equation. I haven't gotten there yet. And L sub z, operating on theta and phi, well actually it's operating in phi alone, is m sub L h bar times theta phi. And L squared, operating on these guys, is h bar squared L times L plus 1 times those guys. That's the basic behavior of, I mean, it's amazing. This most of chemistry just comes from basically extending upon these ideas, okay? And I think I've said my piece. You get to pick the angular momentum along one axis. You don't know it along the others. And the overall value of the angular momentum, the length of my yardstick when I was saying the guy is spinning. How fast he is spinning or she is spinning. Imagine some confused person living on this stick, okay? How fast they're spinning is fixed for any solution to the Schrodinger's equation. So if I have an electron in an atom, it's got some spin, it's got some rotation associated with it that has a value that you know, and then you know the z part. And one final comment, just one final comment. There's this weird thing about rotations in quantum mechanics. I know the z component of it, but the phi-dependent wave function was so simple when I squared it, it went away. So that's a little bit odd. I have this thing, the wave function is like a donut. Well, I don't know if it's odd. Let me just say what it is. It's like, you know, for many of them, it's a donut or a sphere. It's uniform in z, But in fact, the one thing I know about it is it's rotating about the z-axis. Okay? So it's somehow moving, but I don't see any structure in there that is moving. I.e., the probability density doesn't rotate around. You would normally think if I have something that's rotating, it's because I see it rotating. Quantum mechanically, I don't see any probability modulation, in azimuth, yet that is exactly the axis around which there is angular momentum. All right, I'll stop there. Oh, and I'm sorry, I haven't passed out the homework, so I'll assign it soon, and I will give you an appropriate, if I get it out today, it'll be due the next Monday, which is why.